So you have here negative b squared over 4 actually, if you take this common factor, which means that this b squared over 4 is equal, and cancel that. But at the end of the day, my forces, this is what I really care about. My aerodynamic forces is simply what? Is a matrix times q dot times the velocities, and a matrix times the displacement. If it's times displacement, you call it what? It's times displacement. What do you call it? What's the coefficient of the displacement to give you force?
Stiffness constant.
You what?
Oh, it's there right now. It's on the structural model.
What do you call it? Stiffness. Yes, and this is aerodynamic stiffness, right? So yes, the aerodynamics is providing you stiffness, more stiffness, or maybe less stiffness, right? And what do you call this term? Proportion to velocity? Damping. Very good. So this is C aerodynamic. And I will, because they need to go to the left-hand side, I will just have this as negative and negative. So my equations, my full equations, are now, remember we have mass structure times Q double dot plus, there was no C structure, there was no, but you may assume some structural damping, but we did not assume any structural damping. Now we have added to it the C aerodynamic coming from the right-hand side. The equation was MEQ double dot plus KQ was equal to forces, right? Now the forces, here is how the forces are represented. It's supposed to be in the right-hand side, so I'm moving it to the left-hand side. That's why I have negatives here, so that when they move, they have the right side. So we had K structure here. I will add to it whatever comes from aerodynamics. And what is in the right-hand side now? 0, very good. This is a standard mass spring damper system, but it's just second order, happen to be 2 degrees of freedom, H and alpha. And we will invert it or convert it into the very convenient form, which is a state space form. So I will define 2 states, Q and Q dot. Remember, Q is H and alpha, okay? And I will write down d by dt for all your states, which is Q dot, is equal to some big matrix times your states, which is X, so it's Q and Q dot. So this is like X dot equals A times X, okay? And let's fill in our A matrix. The first equation is trivial. D by dt for Q is simply Q dot. So it's 0 times Q and 1 times Q dot. 0 and 1 in the language of what you see. So this is I, identity. And d by dt for Q dot, which is Q double dot, I'll get it from this equation. So I'll move this guy to the left-hand side and invert M. So here is negative M inverse K, negative M inverse C. M, K, and C are the total. Here the total is structure only, here the total is aerodynamic only, here the total is addition. Okay? If you have a question, please stop me. At the end of the day, I have a very simple model. X dot equals A times X. A matrix, 4 by 4. What does this A matrix have inside? Well, let's see. What do we have? Let's see our matrices. We have mass, eccentricity, inertia, stiffness. These are the system parameters. So these are all known. So what about the lift and moment representation? Let's go and see them. Here is the lift and moment representation. Again, this is A. AB is the location of the shear center, so it's given. A is given. And everything is given. Rho is given. B is the geometry of the thing. U, we have the speed. Okay? We have the speed. So this A is function of the speed U, the travel speed of the airfoil. Okay? Can you tell me when this system is stable and when it's unstable? How can I judge the stability of the system? How can I judge stability?
Eigenvalue.
Eigenvalues of the A matrix, right? Simply. So it's very easy now. I'm going to take a range for the speed u. I'm going to take a range for you, say from 100 to 1000 feet per second, whatever. And at each speed, I will compute the matrix A, compute its eigenvalues. If the eigenvalues all lie in the left half plane, then the system is stable. So for 0u, they are here, or for the smallest u, they are here, for example. Then if you increase u, you can plot how these eigenvalues change as you change. So they will change like this. This is as u increases, okay? You can see at a particular point where your real part becomes what? Your real part becomes what? 0. So at this point, the system becomes unstable. Exactly at this point, the system has a limit cycle oscillation. The system has a sustained oscillation. If you have a pure 0 real part and pure imaginary, you have sustained oscillation, right? Forever, which is the flutter. So this is the flutter boundary. So like I said, here is your homework problem. This is the homework problem. So let's get some. You have mass x alpha, c, which is twice the b for the chord. You have a for the elastic axis. You have I for the inertia. And you have ei and gj. Or let's just, anyway, I gave you in the homework how to compute things from ei and gj. We will not consider that here. Where is control B? Maybe? Yes. So these are givens. We're also giving you how to compute kh and k alpha. So you have kh and k alpha. You have all the system parameters, of course, except the speed. So you can go and construct this thing exactly. At any given speed, compute your matrix, get the eigenvalues, plot them or whatever. Look at the minimum real part, the smallest real part, and check if it becomes positive or not. It has to be negative, right? Becomes positive, then at this point you have flutter. So at this particular speed, this is UF. And this imaginary part at which crosses the imaginary axis, this is what? What does the imaginary part represent? For a pair of complex conjugate like this guy, what does the real part represent and the imaginary part represent? Real part represents what? Real part represents damping. And imaginary part? Frequency of oscillation, exactly. So you can immediately see that the flutter problem is a problem of damping. At the beginning you start with some structural damping. Okay? But then you can see here, even if it's zero structure, that's fine, but it will not blow up. You can see immediately that the aerodynamic loads changes your damping. Okay? So this CA, as you can see from here, this is CA, it is proportional to the speed. As the speed goes up, the modification to your damping goes up. At some speed, the damping becomes zero, and you have sustained oscillation. This is the flutter. So it's not a problem of stiffness. There is other aeroelastic phenomena like divergence. It's a problem of stiffness. Here, flutter is a problem of damping. You get zero damping. Okay, I got zero damping. The imaginary part at this point is the oscillation frequency, omega flutter. Okay? If you do that for this problem using exactly what we did, which is your homework problem, you get U flutter is about 272 feet per second, something like this. And from omega flutter and U flutter, you can compute K, right? Because K is omega B over U, right? So you have omega flutter and U flutter. Get this guy, it's around 2 reduced frequency. So what do you think? Okay, we assumed steady aerodynamics, got the flutter boundary, and the corresponding reduced frequency is 2. Can you imply that yes, my assumption was correct and the flow is akin to steady, is close to steady flow, or not? It's highly unsteady, right? I mean, actually, 0.3 is already unsteady. This is 2. It's two-way unsteady. So steady dynamics doesn't work, and you need to revise your thing. Just to give you an idea of how far your steady analysis can go, there is an empirical relation for Flutter which gives you an estimate that is not too bad, too far away. This is simply mu r alpha squared over 1 plus 1/2 a plus x alpha. So you already know what is A, right? It's the hinge location of the, for us here is the elastic axis shear center, it's given. X alpha is the CG location from the hinge location. Mu and alpha we did not define yet, so mu is the ratio between the mass of your airfoil divided by rho b squared, and you can see it's very expressive ratio, how heavy your airfoil with respect to the surrounding mass that you need to move. R alpha has to do with it's the radius of gyration actually, so this elastic axis, the I, moment of inertia, of any shape can be written as mass times radius of gyration squared. So the radius of gyration, of course, we normalize it by B. This is R. Okay. If you just plug these given to this formula, we get U flutter around 1,003 feet per second. Look at the quasi-steady analysis. 270. This is 1,000. It's two. I mean, it's just very wrong. The K flutter is around 0.47. If this is the correct value, it means that it's unsteady flow, right? If it's 0.1, 0.05, you can assume quasi-steady. But if it's 0.3 and above, it's really unsteady flow, and whatever you get from quasi-steady analysis, this is a typical numbers, okay? We're not making it up. It's really typical numbers. If you use quasi-steady analysis, you will get very wrong results for Flutter. Actually, it can be much more wrong. This is the best result that you can get out of quasi-steady, because we added this term. If you're not cautious enough, and many people don't add this term even, because it's not obvious in the quasi-steady analysis. In the steady analysis, you have this, and you have the left acting at the quarter chord, so you multiply by that, but you forget to take into account this term. If you do that, you will get that there is no flutter for this problem. Actually, there is no flutter. Whereas there is a flutter, and the flutter is that much. If you account for even for this term, still the discrepancy is too large. From here, you can get from this empirical relation. This is an empirical relation. From this empirical relation, you can get good insight. The heavier the airfoil, oh, this is, by the way, this is UF divided by omega alpha b. And what is omega alpha is square root K alpha divided by R. The natural frequency of twisting. Whatever, so just to make it non-dimensional. Okay, so do you want U flutter to be larger or smaller for an airplane?
Larger.
Just think about it in a second. Larger, right?
Larger.
You want the flutter to occur at a very large speed that you will not reach it, right, in flight. To be outside of your flight envelope, actually. Okay? It's interesting that all the research that has been done to delay flutter was reversed in the recent years to just make flutter earlier for energy harvesting things. You know? Of course, it's not applicable for airplanes, but anyway. So we need this U flutter to be larger as possible, outside of our flight envelope. You can see that heavier airfoil will help you, right? I mean, which makes sense because it's heavy to oscillate. But down there is something interesting here. So actually, the A is negative. You can see here it's negative 0.34. So the shear center is a little bit ahead of the half cone. And X alpha is the distance from the shear center to the center of gravity. So if we move the center of gravity, I'm just reminding you here, this is the thing, this is half core, this is AB to the hinge shear center, and from here to there, this is x alpha b, this is center of gravity. This is already somewhere here, so the A is negative. And if we try to move the CG forward, even ahead of this guy, so it will be also negative, okay? So if we put some lead in the leading edge, which is a very bad idea, but assume that we put some lead here so that now we have the center of gravity moves here. So we have x alpha is negative, A is negative, A like negative 0.34, say x alpha is negative 0.15, so, or whatever. So you can see here that as these guys become more and more negative, the CG moves in this direction. This becomes very, very small, going to 0, right? Which means that the flutter goes up. So actually this was a solution in the 60s to prevent flutter. They put lead in the leading edge, some lead in the leading edge, so that the CG moves all the way and you have no flutter. Of course, when things become more advanced, now we put flutter suppression system, control system, without sacrificing the weight and adding lead. You know, it's the worst thing to do for an airplane. But this was the practical solution in the 60s. I don't know how long it lasted, maybe even after that. I don't know how it lasted. Any question? So then, unfortunately, we don't have time to go to Dorson today. Hopefully next time.